Hello, welcome back. So today we want to talk about the z-score, which is a useful tool in statistics to help us compare values of population and compare values from different populations. So our goals will be able to calculate the z-score for value in a population, understand the formula, then also be able to understand how to be able to use the z-score to make comparisons. So first, let's look on the left what a z-score is. So it's a z-score, or sometimes called a standardized value. It's a number gives you the number of standard deviations that a given value x is above or below the mean. Okay, that's what it tells you. It tells you in terms of standard deviations how far above or below the mean you are. And if you kind of understand how, if you use the empirical rule for a bell-shaped distribution, to kind of give you an idea of how rare this data value would be expected to be. Now, the z-score can be calculated from a sample or from a population. From a sample, it's the data value x minus x bar, the mean, then that number divided by s, the standard deviation of the sample. Or from a population, it's the data value x minus mu, which is the population mean, divided by sigma, which is the population standard deviation. Now, also is recommended around z-scores of 2 decimal places. This is typically because often, especially when people use tables for z-scores, then often those are put into 2 decimal places. Now, what does the z-score tell us? A z-score is expressed as just a number without units of measurement. That's because the units of measurement of x and your mean are in the units per population. So if we're talking about height, it might be height in inches, and your standard deviation has the same units as x or your mean. So for example, if we're talking about the height in a population, then this would be inches divided by inches, which then would be unitless. Now, a data value is considered to be significantly low relative to the mean if it's less than or equal to -2 is a z-score, or if it's greater, significantly high, if it's greater than or equal to 2. So if it's beyond 2 or more standard deviations above or below the mean, beyond 2, it's considered to be kind of an extreme value. So if your z-score is less than or equal to -2, it means it's less than or equal to 2 standard deviations below the mean. And if it's greater than or equal to 2, it means it's greater than or equal to 2 standard deviations above the mean. So those are typically extreme values relative to the data, relative to the mean. If the data value is less than the mean, the z-score is negative since it's below the mean. And since in that case, then the mean would be larger than x. If it's positive, the z-score is above the mean. Okay, because x then would be greater than the mean, be positive value. Then finally, z-score is useful for comparing data from different populations with different means and standard deviations. Let's take a look at some examples over here on the right. Okay, let's say we have a population of some kind, and let's say our mean, our mu, is 68, and our standard deviation is going to be 14.5. Okay, so let's find the z-scores for the following values. Okay, so number 1, let's do 68 itself. Okay, now, so we're going to have that as z is equal to, our data value is, this is our x, so it's going to be, once again, our formula is x minus mu over sigma. Okay, just plug this in. This is our data value, so 68 minus our mean, which is 68, divided by sigma, which is 14.5. Now, if you notice, this is going to be 0 over 14.5, which is going to be 0. Okay, hopefully that makes sense, because in this case, our x value is the same as our mean, 68. And so the z-score tells us how far you are above or below the mean. So if you're exactly the same value as the mean, your z-score would be 0. Now, let's take a look at some more interesting values. This time, let's try 54. Now, 54 is below the mean, so then we expect our z-score to be negative. So Let's again plug this in. I won't rewrite the formula. Let's be right here. So our x value is 54 minus our mean, which is 68. And then that divided by 14.5. So let's calculate this. So use your calculator. So 54 minus 68. Right, this will be negative. So negative 14 divided by 14.5. Okay. That's equal to negative 0.90 to do decimal places. Okay, negative 9. So, as we can see, that's below the mean, and it's close to 1 standard deviation below the mean. All right, number 3. Number 3, let's choose a value of 51. So once again, this is below the mean, so we'll have a z-score that's negative. And we can possibly make a guess. So this z-score 54 was about 1 standard deviation, almost 1 standard deviation below the mean. This should be less than or greater than 1 standard deviation below the mean. So let's find out. So 51 minus 68 divided by 14.5. So we have negative 17 over 14.5. And that, right, as we expected, so it's negative 1.2 decimal places, 1.17. So a little below 1 standard deviation below the mean. Let's do one more. This time, let's do 94. Now, this is above the mean, so we expect it to be positive. It also looks like it's pretty far above the mean, so we expect maybe even a value greater than 2. Let's see. So once again, plug this is our x, plug this in. So 94 minus 68 over 14.5. And so it's going to be 26 divided by 14.5. And that is about 1.79. So not quite 2 standard deviations above the mean. Now, when we say that 2 standard deviations above or below the mean is extreme, that's not a rule. That's just kind of a typical, what people have kind of agreed on. These typical usually tend to be true. So this could still be fairly extreme. Let's do one more thing. Let's imagine we have a bell-shaped distribution. If this was a bell-shaped distribution, I'm sorry, let me try that one more time. So I'm just drawing with this pen, it's a little difficult. So here in the middle is our mean. This is 68. And also, let's draw original distribution. So we had 68. Okay. And then our values were 54, 51, and 94. Now, what we're doing then, and actually I need to move this, our next example, I need to move this. So give me a moment. Now, what we're doing is this is the original distribution. And what we're doing is essentially converting these to a z distribution. Okay, which have the same shape. Okay, and so this is just converting it in terms of z-scores. Let's try and draw the same, but as well as I can. I'm going to try and draw the same picture. Okay, so here in the middle is 0. Okay, and so now, in terms of standard deviations, 54 is about negative 0.9. 0.90. Next, I believe, is negative 1.17, right? The last one was negative or positive 1.79. So these should also be relatively in the same spot. So we're just a way of converting, and this is something's called the standardized distribution. This allows us to think of different things in terms of just the standard deviations. How many standard deviations are you away from the mean? Okay, either above or below. Now, how is one way you can use this? Let's take a look at our next example. And here, what we want to do is be able to compare values from two different populations. So this time, we're talking about two different populations with different means and standard deviations. And basically, we want to calculate a similar value from two different populations, see which one, how it compares to the mean of its own population. Okay, so let's get a little space here. So this one says the height of men in the U.S. is approximately a normal distribution, with mean about 70 inches tall and a standard deviation about 3 inches. Height of women in the U.S. is also approximately normally distributed, with a mean around 65.5 inches and a standard deviation about 2.5 inches. Okay, now that data may or may not be completely accurate or up to date, but that's useful for a comparison. So what we want to do then is we want to find the z-score for a man and a woman who are both 6 feet 4 inches tall. Okay, let's just divide this right here. So for men, once again, our mean is 70 inches, and sigma is 3 inches. So our z-score is going to be for 6 feet 4 inches tall. So 6 feet 4 inches, I should mention. So that's going to be 76 inches tall. So we find that z-score 76 minus 70 over 3. We just plug that in. So and that's going to be exactly 2. So a z-score of 2. So 2 standard deviations above the mean. So once again, that's typically considered to be kind of an extreme value, an unusual value. So men who are more than 6 feet inches tall is kind of unusual. Now, for women, we'd expect that to be even more unusual. So we expect to find even fewer women than men who are 6 feet 4 inches tall. If we look at the data for women, it says, so for women, the population is going to be, also let's put the ZM right here, just to distinguish them, 65.5 inches, a standard deviation of 2.5 inches. So the z-score for women is 60, so it's, let's we expect this to be more extreme. So 76 minus 65.5 divided by 2.5, and let's just go ahead and find that value. Right, this is actually 4.2. As we can see, that is quite a bit more extreme. That does not mean it's twice as extreme as that. Let's don't read it that way. What this does mean, though, is so for men, a man who is 6 feet 4 inches tall is 2 standard deviations above the mean. So that's, quite a bit tall. That's very tall. It's usually can be an extreme value. Compared to its own population, a woman who's 6 feet 4 inches tall is a lot more extreme. Okay, that's 4 standard deviations, over 4 standard deviations above the mean. Okay, so as we expect, and what this comparison shows is there are a lot fewer women based on the standard deviation, based on the mean and standard deviations of each population. We expect to find a lot fewer women who are 6 feet 4 inches tall and taller than we do men. Okay, so what z-score tells us is that 6 feet what it tells us is 6 feet 4 inches is far more rare for women than men. That's basically what we'd expect. Right. And this is a useful comparison tool because we tried, if we didn't make z-scores, just try to look at this data we just mentioned, okay, and just the average and standard deviation data for both populations. You ask the same question, you wouldn't have a really good feel for what the difference was or how extreme or not extreme each one was compared to its own population. But now with the z-score, that allows us to do that. All right, so what we've seen is basically how to calculate a z-score and how to use it to compare data within the same population even, and also across different populations. Thank you. Have a good day.